Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's start. It's a great pleasure to have today's speaker today, Grigory Yaroslavtsev. Grigory graduated from Penn State University 2 years ago, and then he was a postdoc at Brown and UPenn. He was an intern at Microsoft Research, actually different Microsoft researches. He works on in various areas of theoretical computer science, particularly in approximation algorithms and various aspects of theoretical big data. And today he will talk about correlation clustering problem. And this work started here at Microsoft Research. So,
all right, thanks a lot for the introduction, which actually spelled out my name like properly. Very grateful for that. Yeah, so this work actually started as an internship project here at MSR, so I'm very happy to give this talk here, joined with Shruti Chawla, Konstantin, and Salil Shram. And today's talk is about correlation clustering, which I like to think of as one of these happy success stories of theoretical computer science, when the theorists came and addressed a problem which really begged attention. The problem that was developed by these practitioners in the machine learning lab called Whiz-Bang Labs has been a few papers which introduced this model in a semi-rigorous way. And these machine learning people, they noticed that this problem really has to be solved, but they didn't have any rigorous algorithms for it. And then the theorists, Avram Blum, Nikhil Bansal, and Shruti Chawla came and actually formalized what those machine learning people were trying to do, and develop some basic algorithms for solving this problem. And the problem is really so basic that you can explain it easily to a little kid as the following graph partitioning problem. So suppose I give you a graph like the one on this picture. And what this graph represents is similarities between objects denoted as vertices and points on this picture. So if there is an edge between two objects, this means that these two objects are labeled as similar. And if there is no edge between two objects, it means that they are dissimilar. Okay? And the goal is to cluster this set of objects into any possible number of clusters that you can pick on your own, so that your clustering is consistent with this information about similarities and dissimilarities. Okay? I will make everything formal, but for now, let's just look at the solution, which has 3 clusters in it. And I just want you to notice that there are 3 pairs which are violated in the sense that they were labeled as similar, thus, and thus. And one pair which is actually dissimilar, there is no edge, but this pair is inside one of the clusters. So in that sense, this clustering actually makes 4 mistakes. Okay? 3 for cutting similar pairs, and 1 for putting a dissimilar pair inside a cluster. Okay. So in a more formal way, the goal of correlation clustering is to minimize the number of incorrectly classified pairs. And a pair can be incorrectly classified if it's either a covered non-edge or a non-covered edge, as in the first example that we've seen. Know that these 2 types of mistakes are just treated symmetrically. You just add up these 2 types of mistakes. And this is a goal that we're trying to achieve, minimizing this sum. So in this example, the total score is 4 for 1 covered non-edge, 3 covered edges. Great. This is actually the optimal solution for this instance. You cannot do better than that.
Is that easy to see?
This is not very easy to see, but you can convince yourself. Yeah. All right.
Like that means the problem is not in coNP. Is that what you want to say?
That's another way of looking at it. Right. Great. Yeah. So there is no small certificate for me to convince you that that's the case. Okay. Now, for those of you familiar with constraint satisfaction, I just want to say that this can be seen as a mean CSP, but the number of labels is unbounded. The number of labels here corresponds to the number of clusters that you can pick, and because there is no restriction on the number of clusters that you can pick, the number of labels can be as big as the number of vertices. So it's not directly amenable to CSP techniques because of this. Because CSP techniques only apply usually when the number of labels is very small. Okay. And since the original introduction of this problem in 2004, there's been a lot of progress on it. So the original paper by Blum, Bansal, and Chawla gave some constant approximation, which was pretty large. And by approximation here, I just mean the ratio between the number of mistakes that the algorithm makes to the optimum solution cost. To make sure. And since then, there's been a lot of progress, a number of papers, which ended up achieving 2.5 approximation in the paper by Ailon, Charikar, and Newman. This problem is also known to be so-called APX hard, which means that you cannot achieve an approximation which is arbitrarily close to 1 in polynomial time. But the constant in the hardness is very close to 1, actually. It's 1.00 something. There is also a complementary objective. Instead of minimizing the number of incorrectly classified pairs, we can look at maximizing the number of correctly classified pairs. And that is usually much easier to do because there are much stronger lower bounds on this objective. So complementary objective, much easier to optimize. And even in 2004, we already had a polynomial time approximation schema for that. So today I will focus on the minimization objective. And during the 10 years of existence of correlation clustering, it has become one of the most successful clustering paradigms due to a number of advantages that it has over other clustering methods. So one such advantage is that it only uses qualitative information about similarities between objects. Note that the only data that I had to collect to run a correlation clustering algorithm was information about comparisons between vertices, about objects in my data set, whether they're similar or dissimilar. You can compare this to other popular clustering methods. Like, for example, if you want to cluster using k-means, which is one of the main vehicles of machine learning, then what you need is you need a d-dimensional vector for each point. You need to embed your points into d-dimensional Euclidean space. And this is a lot more information than what correlation clustering uses. Another interesting feature of correlation clustering is that you don't really have to specify the number of clusters in advance. The number of clusters is going to be selected by the algorithm itself to best fit the data that you have. It's one of the questions that usually comes up with k-means, for example, is how do we pick the value of k in k-means? And if you don't know what is a good value of k, maybe you try all of them, which increases the running time, or you guess it somehow and you hope that it's a good guess. But here the number of clusters is really produced as an outcome of the algorithm itself. You don't have to worry about it. One of the applications of correlation clustering is to document deduplication and image deduplication as well. So the way it works is as follows. So suppose you have a large collection of documents or images, and your friends from machine learning group have come up with a new fancy algorithm for comparing these objects. Now they can tell you whether two objects are similar and how similar they are. But they don't really have any rigorous guarantees about this comparison measure. It can be quite inconsistent. Like, for example, in the example that we had, the triangle inequality, for example, did not have to hold necessarily. Like, if A and B are similar, B and C are similar, does not necessarily mean that A and C are similar. So the black box algorithm that we're using here, we don't require any guarantees from this algorithm. So we can use for deduplication any machine learning algorithm that spits out a number about comparison between objects. Great. So since the original paper by Bansal, Blum and Chawla, we know that the problem is NP-hard. And there are some simple approximation algorithms for it that have been developed. And pretty much all the algorithms that I'm going to describe today in this talk will be pretty simple. So using them in practice is actually pretty easy. They're not that complicated. And for those of you who know something about learning theory, I just want to throw in these buzzwords that you can see correlation clustering as an agnostic learning problem. It is an agnostic. Yeah, you have a question?
Yeah, no, please finish your sentence first.
Thanks. You can see it as an agnostic learning problem in the following sense. That we're trying to feed a concept from the class of all clusterings to the data. And unfortunately, in this case, there is no concept necessarily that perfectly fits the data, that makes zero mistakes. Like there is not necessarily no clustering that makes zero mistakes in this case. So the optimization goal here is with respect to the clustering which achieves minimum possible number of mistakes. And that's exactly the agnostic learning side. Yeah.
So I have a question. You were mentioning that these algorithms are very simple and so on. If I remember correctly, this original one with Blum and so on,
yeah, that one is an exception.
Definite, relaxation,
right.
Which is something that you could never do on a reasonable amount of points just because it's hard. So you mean simple in the sense that you just say, so like the later algorithms, do they also use PSD solver or?
So for the algorithms that I'm going to describe for that specific objective, you actually don't need semi-definite programming. So.
But Blum did use it in 2004.
So for some other variants of this problem, you do need semi-definite programming, and these are the problems that I believe you're referring to.
That are what? I'm sorry.
I believe you're referring to some other flavors of this problem where
these do not.
For this specific variant, you don't need semi-definite programming.
And I have another question. We're already talking about the history. How many of these different, through the 10 years of work, do they also allow to have weights on the edges?
Yeah, I'm going to talk. That's a good question. I'm going to talk about weights later. Some of them do, some of them don't. I'll treat this topic later. Okay. All right. So if you want to learn more about this, then I'm going to describe in this talk. Then you can check a survey by Anthony Wirth. There was a KDD tutorial about correlation clustering and all sorts of flavors and toppings on top of it. There's a Wikipedia article. That should be enough, I hope. All right. So now let me move on to the algorithms. And the first algorithm that I'm going to describe is something that I'm going to call database randomized pivoting. So this algorithm was developed by Ailon, Charikar, and Newman, and it achieves a 3 approximation to the mean disagree objective in expectation. In expectation, because it's a randomized algorithm, the randomness is over the choice of a random bits of the algorithm. So here's the algorithm. It's very, very simple, as we promised. You pick a random pivot vertex, let's call it V. And for the rest of the talk, all the pivot vertices that I'm going to use will be purple. Then you make a cluster consisting of the vertex V together with a neighborhood of V in this graph. So this is the first cluster that you pick. You set it aside and recurse on the rest of the vertices. So remove this cluster from the graph and repeat this process again. So very simple algorithm. You can implement it in almost linear time easily. It's very, very, very practical, but pretty sequential if you look at this, because you have to pick these pivot vertices one at a time. And in the worst case, it might take you a linear number of iterations of this process to produce the resulting clustering. So I just want to mention that there is a parallel modification of this algorithm which achieves a slightly worse approximation, but can be efficiently parallelized. Specifically, in MapReduce model, it runs in polylogarithmic number of rounds, and this is a recent paper which appeared at KDD. I have a blog post about it, which is going to rigorously introduce you into this model of MapReduce and tell you what the algorithm really does in that case. But this algorithm is so simple that it can be actually done in MapReduce as well. Great, so let's see an example of how this works on this toy graph. So we pick a pivot vertex P, the purple vertex over here, and it grabs together its neighborhood in the first cluster. And then we recurse on the rest. Uniformly at random pick a vertex from the rest, this purple one, and construct the second cluster. And now we just have two singleton vertices, so we just finish off by picking clusters of size 1. And as you can see in this example, we did cut 6 edges and put 2 non-edges inside. So we made 8 mistakes, which is a true approximation to the objective that we're trying to optimize. And that's pretty well. OK, so now let's look at this problem from a different perspective. In order to come up with a proof, I want to introduce an integer program for correlation clustering. So the same clustering problem as before can actually be expressed as an integer program of the following form. So this may look complicated, but let's go over it step by step. The idea is that we introduce a binary distance, x uv, between all pairs of vertices. This is binary in a sense that x uv's are 0 or 1 only. The interpretation of the binary distance is that if x uv is 0, then u and v are in the same cluster. Otherwise, they are in different clusters. Now, using this interpretation, you can convince yourself that the objective is exactly the mean disagree objective that we had before. Because we add up over all edges x uv's. So we pay 1 if u and v are in different clusters. And 1 minus x uv for the non-edges. Finally, we have this triangle inequality constraints here. And because x uv's are binary variables 0 or 1 only, triangle inequalities are equivalent to transitivity constraints. So if x uw is 0 and x wv is 0, then x uv is also 0. So this means that any valid integral solution to this program actually induces a partition in a clustering of the set of vertices. And that's what we're looking for. Great. So the equivalence classes of the relationship u and v are the same if x uv is 0, actually form a partition. And this is the same as what we had before. Now, we don't know how to solve integral programs in polynomial time, so we do the standard thing, relax it to a linear program. So instead of using 0, 1 variables, we're going to use variables which are real between 0 and 1. And a solution to this program now gives an embedding of the vertices into a pseudo-metric. I'm using this term pseudo just to highlight the fact that it could be the case that two vertices coincide. Yeah, sorry.
I have a question. Could you go back to the slide, please? So are you assuming that there can be more than 2 clusters, right?
Yeah, there can be any number of clusters, because this equivalence relationship can have any number of equivalence clusters.
I'm sorry for maybe saying something.
Yeah, sure. It might take some time to grasp.
So you're saying that xuv is 1? Oh, if they're in different clusters.
That's right. It's like a distance. If you're distance 0, then you're the same thing, and you're in the same cluster. If distance is 1, you're in different clusters.
I thought it was 1 if they're in the same cluster. I see. Okay, good.
All right, should I go on?
Okay.
All right.
Yeah, I apologize.
All right. No worries. All right, so we got an embedding of vertices into a so-called pseudo-metric. And it's exactly the same as just the usual metric, except that some points are allowed to be a distance 0. That's what pseudo is referring to. And now let me show you that there is a gap between the objective values of the integral and linear program. This is called the integrality gap of this program. And I'm going to show you that it is at least 2 minus some little of 1. There is a simple example that illustrates this. it is a star consisting of edges, two vertices, which are disconnected from each other. Now remember that a solution to an integer program is exactly the same as a clustering, and the best clustering here that you can construct looks like this. You just pick one cluster of size 2, and the rest of the vertices form singleton clusters. That's the best you can do here. This gives the cost of the integer program to be n minus 2. But the linear program can cheat in the following way. The solution to the linear program can be constructed as follows. You just put 1/2 on every edge of this graph and 1 on every non-edge of this graph. So note that because all the values are either 1 or 1/2, then the triangle inequality is satisfied for every triple. And the objective value is just roughly n over 2, because we only pay for the edges in this graph, and we pay 1/2 for edge. Because the non-edges are distance 1, and they are OK. OK, great. So this is the integrality gap. And this also means that we cannot achieve approximation factor better than 2 if you just use only linear program as a lower bound of the optimum. Now, the question that we asked in our work was whether we can actually match this integrality gap and achieve this approximation factor, which is roughly 2. And the answer is almost. So we can achieve a 2.06 approximation, which is within 3% of the integrality gap. So remember that the previous one was 2.5 approximation. I'm going to introduce some other results that we get later formally, but for now let me just informally say that we can also use our technique for a bunch of related scenarios, achieving approximation for clustering objects of k different types. So suppose instead of having just objects of one type, as we had in this example, we have objects of k different types. And we can only compare pairs of objects of different types with each other. In that case, we have a match in 3 integrality gap. The previous one was 4. And I'm going to talk about the weighted case, the one that you asked me about later, but only about some specific version of the weighted case in this talk, because the general version of weighted case is actually pretty hard. For the case when weights satisfy triangle inequalities, we get 1.5 approximation. There is an integrality gap of 1.2 that we show. So the new results are bold in this slide. That's the point of bold here.
Sorry, what's the second point? K-types? What was that?
So suppose that you have objects of 2 types. Suppose you're Netflix, and you have information about comparisons between people and movies, which people like which movies. But you don't know which people like which people because you're not Facebook, and you don't know which movies like which movies because it doesn't make any sense. So you want to cluster movies and people using this data. All right, so
So you can do that.
yeah.
Like the definition of your weight, it doesn't generalize the above one. Of course, your factor is anyway better, so it shouldn't generalize. But okay.
Yeah, I mean, the problems in this slides will be rigorously defined later. Unfortunately, not right now, because I'll need to introduce some notation before I can do that. All right, so so the next algorithm that we're going to see is the one that actually uses this linear program. And I will call it a linear program-based pivoting algorithm introduced by Ailon, Charikar, and Newman again. So this is the one that achieves 2.5 approximation. So it's similar to the basic pivoting we've seen before, but it uses a linear program. So first you solve the linear program, and you get these values x, u, v, which I'm going to informally call distances. And then you do a similar pivoting process as before. You pick a random pivot vertex, so let's call it P. And now you form a cluster of P together with a randomly chosen set. I'll call this set S of P. The randomly chosen set contains every other vertex with probability which is 1 minus the distance. So the reason for that is pretty simple. We want the vertices which are close to be in the cluster with P with probability very large. And if they are far, the probability should be small. So here is just a linear function of the distance, 1 minus the distance. And note that these decisions are made independently for each of the other vertices. Okay? And then we make a cluster consisting of P together with this random set S of P. And we just recurse on the rest, as before. Great, so this is the algorithm. And let me show you how this algorithm works on the integrality gap example, because this will be important for later. So remember that in this star-like example, the LP solution XUV can look as 1/2 on edges and 1 on non-edges. So the LP cost is roughly n divided by 2 here. And now let's look what our algorithm does in this case. So the algorithm picks a random pivot. So suppose the random pivot is chosen to be one of these vertices, which are the spikes of the star. So the I is here. So this happens with probability which is almost 1 in this example, 1 minus 1 over n. So in this case, with probability 1/2, we pick a singleton cluster. And with probability 1/2, do I have animation for that? All right, so with probability 1/2, we get a cluster of size 2. And with probability 1/2, we get a cluster of size 1. So if we get a cluster of size 2, if we cluster this edge together, then we get pretty much the optimum cost, because we just cut this edge away, and the rest is just singleton clusters. On the other hand, if we just cut a singleton cluster consisting of this vertex, then let me informally claim that we made no progress whatsoever. We did cut away one vertex, but in the bigger picture of things, it doesn't matter at all. So this is why I just want to say that expected cost condition on Vi being a pivot is just 1/2 of n plus 1/2 of the original expected cost. Okay. So the other case is when we pick the central vertex of this star to be the pivot, which happens with probability 1 over n. It's a very small probability. But unfortunately, if we do this, then we have to pay a lot. Because by concentration bound, we cluster roughly half of the vertices together with the pivot. And that means that we grab a quadratic number of non-edges inside the cluster, roughly n squared over 8 pairs, which are non-edges, will be inside. And that means that we pay a lot here. So solving thus for the expected cost, putting this all together, we can see that the expected cost in this case is roughly 5n divided by 4. Which seems not that bad compared to the optimum, which is roughly n here. But remember that if we just use in linear program as a lower bound, we are already losing a factor of 2. So comparing this to the linear program in lower bound, we already lose a factor of 2.5. And this is exactly what the Ailon, Charikar, and Newman analysis matches. Great. So you cannot do better than 2.5 this way. All right. So here is our idea how to improve this. So the generic schema will be very similar, but we go into account for this issue that we had in the previous example. When we pick in the randomly chosen set S of P, our decision about including a vertex into S of P is going to depend on two things now. Not just on the LP value or the type of the edge, but on both of them. So remember that we have seen two algorithms before. One made the decision just based on the graph alone without looking at the LP value. So it rounded the vertex together with P if PV is an edge and did not round otherwise. So this was the first algorithm that we've seen today. The second algorithm was using the LP and just set this function f to be 1 minus x PV. Okay. So let's try to use both. So here is the function that we use. The function makes a distinction based on whether PV is an edge or a non-edge in the graph, and applies different rules based on this. So if it's a non-edge, it's the same rule as in the LP-based pivoting, 1 minus x PV. If it is an edge, it is 1 minus some function f plus of x PV. The function f plus is some carefully chosen function. Is some piecewise quadratic function, which is 0 up to the point 0.19, and 1 after some point b, which is roughly a half, but slightly greater than a half. And in between is just some quadratic polynomial. Okay? And note that the fact that we cannot get an approximation factor of 2 really comes from the fact that this b is really a little bit above a half. Which means that in that example, when we pivot from the central vertex, we're still going to round a really tiny small fraction of vertices together with u. But they're really, really tiny. That's something that we're really trying to minimize here. Okay.
So you would not be able to still get 2. That's what
right. That's the reason why we get 2.06, but not exactly 2. Okay. So there is actually some kind of conflict in reason, which does not let us make this function to be 1 all the way at 1/2. And it will come from the analysis.
But this is pretty crazy function. It's clearly
It's a pretty benign function. It's a piecewise quadratic function. Yeah, it's something that you study in your 7th grade, right? You already know what quadratic functions are. It's not too bad. All right. All right, let's see. So now let's move on to the analysis and see where this comes from. All right, so for the analysis, let's break the execution of the algorithm into stages and look at one stage at a time. So remember that at every stage, we just construct one cluster. And we start with a set of vertices V. There are two things to keep track of. ST is a cluster constructed at step T, and VT is a set of vertices which were still not processed when we started step T. So V1 is exactly all vertices, S1 is the first cluster, V2 is what is left after the first cluster, and so on and so on. So important to keep track of these two notions, ST and VT for the rest. So let's look at the analysis. We're going to break it into stages as follows. At every stage, we have the set of vertices Vt, which is still unprocessed. We pick a cluster S sub T from it, and the set of vertices Vt plus 1 is still left unprocessed. And let's break down the cost that the algorithm pays into these stages as well. So suppose we consider this stage T. Let's analyze the cost of the algorithm at this stage. What the algorithm does at stage T is it makes commitments to make mistakes on two types of pairs. There are edges in the graph which will get cut when we pick the cluster ST, and there will be non-edges in the graph that will be put inside the new cluster ST. These are the two types of mistakes that the algorithm commits to make when it picks the cluster ST. There are no other mistakes that it has committed to making so far. Okay. And let's just add up these two types of mistakes. So for all edges UV which are still left unprocessed, in expectation, the probability that we separate the endpoints of this edge is just the probability that we put one of the endpoints inside and the other one outside. And for the non-edges, it's just the probability that we put both endpoints inside. So this is this expression. Now let's compare this to the specifically designated part of the LP that we can use to charge these mistakes that the algorithm makes. So we will use the following part of the LP to charge these mistakes. I will denote this as LP sub t, the part of the LP that we use at step t. And the idea here is that we can use the pairs in the LP such that at least one of their endpoints is inside our new cluster. Because these are the pairs that sort of can be attributed to this cluster directly. And each such pair will be attributed to only one cluster, so we never overcharge. Great. So if we use such pairs whose at least one endpoint is inside the cluster, then we get contribution from edges. And the contribution from edges is xuv, if you remember the objective. For non-edges, it is 1 minus xuv. Each of them is just multiplied by the probability that we get the contribution from this specific pair. And that probability is just that we get one of the endpoints inside. Okay? Great. So this is already something. And we've been able to break down the comparison between the cost of the algorithm and LP into these stages. So it just suffices to show that the expected cost of algorithm at iteration t is at most alpha the cost of the LP at iteration t. And then we just add them up over all iterations, and then we're done. Great. So this is indeed already something, but it's still too complicated to analyze these things because there are so many things going on. The next idea is to break down each stage into something very, very simple, into analysis of just triples of vertices. So this is what I'm going to call triangle-based analysis. So let's just focus on a triple of vertices for now, and then I will put this together. For a triple of vertices, u, v, and w, where w is a purple vertex, so it's a pivot, let's look at the expected error that we get on a pair uv if w is a pivoting vertex. So here's a picture. Suppose we have a triple of vertices where w is a purple pivot vertex. If uv is an edge, then we make a mistake on this edge if we cut one of the endpoints together with w and the other one not, if we cut this edge in this clustering step. So there are two types of situations like this when we cut either u or v together with w. Okay. So is this clear? Just to make sure, because it's kind of complicated. Okay. Now, if uv is a non-edge, then we only make a mistake if we grab all the endpoints of u and v together in the cluster with w. And if you remember what f means, then f really captures the probability that we grab the endpoint together. So these are just probabilities of these two events. Okay. Great. And the same reasoning can be applied to the LP. The LP contribution for the triangle UVW is as follows. The LP contribution can be used in this triangle if we manage to cut away at least one of the endpoints. So there are three cases when this happens. When we cut one or two of them, and the probability that at least one of these happens is given by this expression. If this happens, then depending on the type of this pair, we get different contributions. If this pair is an edge, then the contribution is xuv. if the pair is a non-edge, then the contribution is 1 minus x uv.
So yeah, I don't understand why do you have this thing in the object in front of xuv? What is that? The expression?
So this is the probability that we can use the contribution of the LP for this triangle. So remember that we partition the cost of the LP between iterations. Yeah, okay.
Yeah.
Okay. So the only way we cannot use the cost of the LP if we manage to separate U and V from W, both of them. And there are 3 cases when this doesn't happen. Okay. Great. So the last trick is to express the cost of each iteration in terms of these triangles that we have seen. And this is very simple. You just write the expected cost as the sum over all pairs UV, which are still not processed. For each pair, the expected cost of this pair is the following. Because we choose the pivot W uniformly at random, we choose a specific W with probability 1 over the cardinality of Vt. Conditioning on W being the pivot, the expected cost of UV is just this expression L W UV, which was on the previous slide. So thus, summation really is the expected cost of the algorithm at iteration t. Now we can rearrange these summations, and instead of adding up over UV and then over W, add up overall triangles UVW. Then we double count each such pair, so there is a factor of 2 here. And we end up with a summation of these expressions LWUV. The key part of the trick is to reduce everything to just triangles. Exactly the same can be done about LP because just a summation. Thus, it just suffices to compare ELG and LP on triangles only. And this is something that is actually manageable. Now, you only have to show that this relationship holds for triples UVW. But it's still not that easy. So we want to show this for all triangles. But remember that for each triangle, we can have, first of all, one of the possible edge non-edge configurations. So a triangle is specified by edge non-edge configurations and the LP values that are assigned to its sides, right? So we need to show that this relationship holds no matter what the type of the triangle is, no matter what the LP values are, as long as they satisfy the triangle inequality. The type of the triangle is fairly easy to deal with. You just enumerate 4 possible types. But the LP ways satisfying triangle inequality form a search space which is a 3-dimensional space, right? So it's not that easy to enumerate over. This is where our paper sort of gets rough, right? And you have to go through some case analysis and convince yourself that actually there is a way to choose a function such that this holds. Okay, remember that here we have flexibility in the choice of the function also. So first we choose a function, and then we show that this holds. So I encourage you to go and read our paper. You know, this is where the interesting stuff is. How do we actually deal with this problem? But eventually, we managed to show that for every fixed configuration and every set of weights which satisfies the triangle inequality, this holds. And the alpha that comes out of the analysis is 2.06. Moreover, we can show that no matter which function f you pick, using this analysis, you cannot get better than 2.025. We can actually push this up, I guess. But the point is, you cannot really get all the way down to 2 using this analysis.
So a function which only depends on the edge type and the LP value.
Right. Yeah, this all applies only to this framework where you use this type of function.
And you try to analyze it triangle to triangle.
Right, yeah, exactly.
Do you do a computer search to find the function f?
Yeah, initially we had to do some computer search to find it.
And what type of structure were you looking at? Like quadratic functions like this, or?
Yeah, we were trying to come up with some simple polynomial, piecewise polynomial that would fit the bill.
But did you restrict to quadratic or did you go higher?
We tried higher polynomials, but the improvement was kind of marginal. So.
But you did get an improvement.
I guess maybe you can improve a little bit, but it's sort of the point here is that you cannot really get all the way down to 2, and we are pretty close to the limitation of this approach. So it's kind of a trade-off between your time.
So that's why you didn't.
Yeah.
In fact, we have a bigger lower bound, so that again, using kind of more like numerical search, it's easy to prove a trivial space as well, but it's just maybe not that important. Something like 2.0 something is also low bound, so there is very small gap.
So that I don't understand how you prove those lower bounds, but how do you do a computer search?
Will you go over?
Yeah, I won't go over this unfortunately.
The low bound again sort of follows from this expression, sort of you write it for different triangles, you get some inequalities, so that somehow. Again, this is only for this framework, so it's possible that if you analyze somehow differently, you can get to using different functions.
Yeah, so the analysis sort of focus. There are some kind of triangles that you can show are bad, and for those specific triangles, they will have very specific configuration of lengths. For example, the triangle inequality has to be tight for them. That gives a lot of restrictions, and moreover, they're going to have equal lengths. They're going to be isosceles triangles. So that limits the search quite a bit. Well, the type of triangles that we use are those type of triangles. What's that?
Some of those.
Yeah, some of them. So. Okay. So then you can actually analytically handle this. Instead of like having function of 3 variables, you only use 1 variable basically to control your triangle, right? Because it has 2 other restrictions. Like it satisfies triangle inequality and is isosceles. So then it becomes a function of 1 variable only, and you can analyze it.
So the analysis for factor 3 and 2.5 also went just by analyzing the same expression for triangles, or do they?
Right, but for them the problem was easier because they had the function fixed. They didn't have to do search of the function space.
That's what like, but it
Right,
can't be like it is.
Right, yeah. So the framework was similar, but they didn't have to do the search of the function space. All right, cool. So the setting that I described is usually referred to in the literature as complete graphs case, because we care here about all pairs in the graph. So in the objective, we add up over all pairs in the graph. And we get 2.06 approximation for this case. It can be de-randomized, which is actually not that trivial in this case. There was a previous paper by these guys which de-randomized the 2.5 approximation. This 2.06 approximation also works for the case when there are real weights which satisfy the so-called probability constraints. So remember that in the setting that I described, all weights were sort of either 0 or 1, right? But now suppose in the objective, in front of each term, there will be a weight, CUV, and the weights corresponding to XUV and 1 minus XUV are complementary. So XUV is multiplied by 1 minus CUV, and 1 minus XUV is multiplied by CUV, and these are the weights. So in the previous case, these CUVs were either 0 or 1. If you allow them to be real, then everything also works. In the special case, when these CUVs, you should really think of them as some empirical distances. So it's natural to assume that they might satisfy triangle inequalities as empirical distances. In this case, you get a better approximation. So we get 1.5 approximation using some different carefully chosen rounding functions, not the one that I had before. And the integrality gap for the triangle inequalities case is 1.2.
Yeah. So that is what I was
Yeah.
So somehow, like when you introduce a weighted, it should there should be a natural generalization of the previous one you said, right? But this doesn't generalize what you just explained to us.
It does actually. So
So
see, the point is that if you start,
Just that without triangle inequalities, the weighted version is so hard. So he introduces triangle inequalities, and that's why it is simplifying.
that's also true, but Mahit, addressing your question, does generalize because if CUVs are 0 and 1, so those points which have CUV 1 are non-edges, and those points which have CUV 0 are edges.
Yeah, but they need not satisfy triangle because they need not satisfy triangle inequality, right? In your previous.
Right. So this is what I call just probability constraints on them. And this is generalization, strict generalization of the complete case. Yeah.
No, it should not. You're getting a better approximation, right? So you can't.
If they also satisfy something extra,
Okay.
which should make sense, right? They satisfy something else.
You mean the triangle inequalities?
That's right. Like those previous 0-1 weights, they did not satisfy triangle inequalities because there could be, inconsistencies, right?
Yeah, no. My point is that when you say weighted, you intuitively want to generalize the unweighted. You want to capture the unweighted instance as a special case.
Right.
But by introducing these triangle inequalities, you do not capture that anymore. Huh?
Yeah, so the weighted case itself, of course, like what's called weighted case, generally doesn't satisfy triangle inequality. And then the problem doesn't have a good approximation. I think log-n approximation is the best, and somehow the problem is similar to multi-cut in some sense. Yeah. So this sort of, if you add triangle inequalities on the weights, then the problem becomes actually easier than in the complete graph, because you can't have those bad triangles. So sort of you can't have, two similarities and dissimilarities in between.
Yeah.
So this is actually a very strong constraint.
Yeah.
I don't know whether you can, expect it in practice or not, but it is a very strong constraint. Yeah.
Mm-hmm. Okay. And I was referring to this item before about objects of k-types. So now suppose that in the objective, we only count contribution of pairs which are edges in some graph. So we don't care about all pairs now, but only about those which are edges in some graph. And when we have objects of k-types, this graph is very specific. It's just a complete k-partite graph. So in this case, we have E, the set of edges of a complete k-partite graph. Like in the Netflix example, this is a complete bipartite graph. And we only sum up contributions in the objective which correspond to edge pairs. So this is a more general case. And we get a 3 approximation here, again using some different rounding functions. And we have a matching 3 integrality gap. All right, thanks for your attention. Let me just wrap up with some open problems here. There are 2 main directions for open problems. One is getting better approximation. And it's natural to expect that maybe stronger convex programming relaxations can help us here. For example, if you use a natural semi-definite programming relaxation, then the integrality gap is 3/2, at least 3/2. It's natural to ask whether linear programming, semi-definite programming hierarchies can help us reduce the integrality gap even further. Another question is sort of the opposite of that. Can we achieve better running time while maybe compromising an approximation or keeping it the same? Can we avoid solving the LP? This is the technical obstacle that is the most computationally complex part of this algorithm. Can we get less than 3 approximation in parallel? And let me just mention that there are a few related scenarios. There's a very specific flavor of this problem called consensus clustering. Let me not describe it actually, but just to drop it here. And as I think Kosti mentioned before, the most general case of this problem where there are weights which don't necessarily satisfy triangle inequalities or any other constraints whatsoever is actually pretty hard. It's as hard as multicut, and getting a constant factor approximation would disprove UGC. So it's a good way to work on UGC. All right, thanks.
What is the hardness? No?
Well, I asked a number of people what the ABX hardness is. No one knows. Something like 1.00 something, and no one knows what it is really. So, because it's reduction from some complicated problem, and no one knows what the hardness is. But it's very close to 1.
It's closer to 1 than our result to 2.
What is consensus clustering?
Consensus clustering is a special case of the triangle inequalities case, so the one for which we get 1.5. But the one when your weights are generated according to some specific process. Let me describe the process to you. The process has taken a convex combination of clusterings. Okay? So every clustering is a 0-1 distance measure. So suppose you have a bunch of clusterings coming to you from somewhere. And you want to come up with a single clustering which somehow is a consensus between them, something that represents them all. What you can do is you can take a convex combination of weights given by each of these clusterings, put them together. Because it's a convex combination of weights, it's going to satisfy triangle inequalities. And that gives you an instance that you want to solve. So you will get 1.5 as an instance satisfying triangle inequality does. But you can actually do better because the instance is generated using some specific rule here. You can get 4/3 using the Ailon, Charikar and Newman approach. The question is, can you do better? All right.
So I'm also sorry about that. Given such a instance, given such a distance, can I actually also get back these clusterings as well? Is that easy?
No, I don't believe you can do this.
So-
because I mean, it's information, like it's a one-way information loss, right? You get a cluster instead of a collection. So I'm pretty sure it's impossible. It's a good question though, but I'm pretty sure that's impossible. Yeah. Mm-hmm. Right.
Questions? Take the speak again.